Thank you. So welcome everyone to this seminar. So as it is now a common trend for our UNSW Statistics Seminar Series, it's also under the umbrella of Statistics Across Campuses. So today we're very happy to have Geoff McLachlan from the University of Queensland to give us a talk. So a brief introduction of Geoff. I guess many of you know him or have heard of his work previously, but so Geoff does research in statistics. In particular, he's doing research in classification, cluster, and discriminant analysis, but also like statistical inference. And in particular, he's looked at application of finite mixture models and estimation using the EM algorithm. Today, Geoff is going to talk about semi-supervised learning of a classifier from a statistical perspective. So thanks, Geoff, for accepting to give this seminar, and the floor is all yours.
Well, thank you very much, Boris, for the invitation to present the seminar. I must apologise for my lack of computer know-how to link without this problems. I actually did teach using Zoom the entire last semester online using Zoom, but it didn't seem to help me today in trying to get on. And well, I hope everyone who's in New South Wales or Sydney is coping with lockdown. Well, this seminar is on joint work with my UQ colleague Daniel Arfock, and indeed it was Daniel who suggested that one should look at modelling the missing data mechanism for the labels of the unclassified observations. And so that forms the basis of the main result of this seminar. So, before I go off the homepage, the references to our work can be found on my homepage here, where I have a list of my publications. But as I was saying, Daniel provided the suggestion which forms the basis of the main result of this seminar, and to summarise the main result, it's just the title of our paper in Statistics and Computing, and that is a classifier based on a partially classified sample can have a smaller expected error rate than if the sample were completely classified. And at least it seems to me that this is a very surprising result, I thought. But and so let me explain briefly how it comes about. So I'm saying that we've got a partially classified training set. So I'm in a discriminant analysis or a context where we've got predefined classes, and we want to build a classifier to assign some new entity to one of these classes on the basis of some measurements made on the entity. So throughout this talk, Y here denotes a vector of feature variables. It's the what we measure on the entity to be assigned to one of the classes, and it's got a label which I'll call Z. It's a vector because I'm going to, if there are G classes, it's going to be a vector of G zeros, except in one position it'll have a 1. So if it had a 1 in the third position, it means that the feature vector came from the third class. Now it's partially classified because not all the feature vectors have their labels. Some are missing. And by classified here, I mean that they're labelled, and I'm assuming that they're the ground truth labels. I'll say something at the very end when they're not. But so I'm using the word classify in the sense of that they've been correctly labelled. Now, as I said just a while ago, it was Daniel's suggestion that we follow the framework of Rubin when you've got missing data. And in the present context, the missing data is a label. So we introduce a indicator variable, MJ, which is 1 if the label is missing and 0 otherwise, that is, if it has been observed. And we're focusing on estimating the Bayes rule. So, and I should say, with this missing data mechanism that we're introducing into the problem, we define it in terms of the conditional distribution of the random variable corresponding to this indicator variable, given all the data. The data includes the observed data and data that hasn't been observed. Now, just some terminology in some acronyms. In the framework that Don Rubin put forward, we have MCAR that's missing completely at random. So the probability that this random variable is 1, that is the ZJ is missing, given YJ and ZJ, doesn't depend on YJ or ZJ. It's a constant, or it could be a function of some parameter xi, but this xi is distinct from the parameters that we're using to form the classifier. And now we've got missing at random, where this probability that the label is missing, given the YJ and ZJ, is a function of YJ, what's been observed. It's a function of what's been observed, and it could have some parameters here. This xi means it's distinct from the parameter vector theta. Theta is the vector that we need to know to form the Bayes rule. And then we've got MNAR or NMAR, people tend to use both, where the probability of a missing label depends not only on the observed feature vector, but also on the unobserved value of the label. But we're not looking at this in this particular work that I'm talking in the seminar. We're looking at this particular case. Oh, I should say, if we didn't have a theta here, then we can ignore this. We can ignore the missing data mechanism. That is, the likelihood formed, ignoring it, is the same as the full likelihood. The only thing is, it will have a different distribution. So if you're going to try and calculate the Fisher information, you have to not ignore it. So just a few brief introductory remarks about semi-supervised learning. There's been, I think, a recent revival of interest in semi-supervised learning, and it's come about because a lot of people, not so much, I don't think, statisticians, but people more in the computer science area, have got some impressive results, at least in an empirical sense, on some benchmark image and text classification data sets. But from a statistical perspective, the theoretical understanding of these modern semi-supervised learning algorithms is still limited. I suppose the title of my seminar is misleading. We're not going to try and look at these methods in a statistical framework. I'm using a statistical framework to construct a classifier in a traditional statistical sense. And so, well, as I started a bit late, I better hurry through this. But there's methods for semi-supervised learning. They involve these various things here. People talk about consistency regularization and other methods of regularization. And all these methods, used in conjunction or not all used together, they create a paradigm where unlabeled data can be useful in the formation of a classifier. And the idea is that it's hard to get correctly labeled data. It could be expensive either in time or in cost or both. And say in a medical sense, it may not be possible to actually determine the true class of origin for some clinical values. It may be that it's not ethical to perform some invasive technique for a person having certain feature values. So the idea is we try and get the extra information by gathering a lot of unclassified observations. As I say, there are many open research questions which I'm not going to address today. Now, we were invited to write a paper for an issue of this new journal, or relatively new journal, Econometrics and Statistics, to celebrate the 20th anniversary of these meetings in London. But and we do cover a little bit of some of the methods that have been used outside of statistics, particularly by researchers at Google. And there's fixed match, there's rematch, there's mix match, there's remix match. There's a lot of methods, and it's not so easy just to compare one semi-supervised method with another. Some of these methods have about 20 tuning parameters. They're quite involved to get it to work on a particular set. Now, we're looking at, I'm looking today at generative classifiers, and that is, we actually put forward a model for the joint distribution of the features and the labels. And so we can attempt to work out the Fisher information in the unclassified observations. And so we've got a way of actually assessing the benefit of using unlabeled observations. We can actually put forward a theoretical argument. Now, as I said, we're going to estimate the Bayes rule. Well, the Bayes rule I'm denoting by R. So this is an entity having feature vector Y. We want to assign it to one of the G groups. Well, this Bayes rule depends on the parameter theta, and we assign it to the class to which Y has the greatest posterior probability of belonging. So these posterior probabilities come up throughout this talk, and I'm letting tau sub I Y theta be the probability that the observation actually comes from the I class given the feature vector Y has been observed, and using Bayes' theorem is given by that. Now, to get some of these theoretical results out, we're going to look at the two-class situation where the covariance matrix is the same and the classes are normally distributed. And in this particular case, discrimination, or the allocation rule, becomes a linear function in the vector Y. And beta naught and beta 1 are defined by these well-known terms. And we can reparameterize this, because in this two-class normal situation with a common covariance matrix, that we've just seen only depends on beta. So the vector of all the unknown parameters consists of beta and some that aren't needed in forming the classifier, and we call that theta sub 1. And of course, in this particular case of just two normal populations with a common covariance matrix, we've got this convenient canonical form. We can take one vector to be 0, the other one to be 0, except in one spot where we've got a delta, and delta is the Mahalanobis distance between the two classes. And we can take the identity matrix to be the covariance matrix. Now, I want to go back a little bit in time, but I will come back to the present century. In the early 1970s, I was doing a PhD, and a very useful paper then was by Michael Hills, who read this paper to the Royal Statistical Society. It was basically on his PhD work. Unusual for a young person like that to read a paper to the research section of the Royal Statistical Society, but he did his PhD under Peter Armitage, who was a professor at the London School of Hygiene and Tropical Medicine, and who went on to Oxford to replace Maurice Bartlett as a professor there. And one of the discussants was C.A.B. Smith, who held the Weldon Chair of Biometry at University College London. And in his discussion of this paper, he said, what would happen if we had a situation, we had a sample where one of the variables at least was looking to be bimodal, and suppose we divide it at the anti-mode, then form a classifier on the basis of the two, on the basis of that partition on the two subsamples we got, reapplied it to the sample, and so on. And he's got as far, and I'm quoting C.A.B. Smith here, He says, as far as I know, there is no theoretical research into the effect of lifting one up by their bootstraps. So when I finished my PhD, I thought I'd tackle this problem and have a look at it. Now, in order to make this problem analytically tractable, I assumed that we had a small number of classified observations. So I actually turned it into a semi-supervised problem. And I assumed that we had lots of unclassified observations, and indeed I let that number go off to infinity. And in the case where the prior probabilities are equal, I was able to get an expansion of the expected value of the error rate. This is the overall conditional error rate of the rule using this estimate. I'm just calling this to be the estimate we get of beta using, well, the way we got this, we followed what Hills did, but it's what's called the classification maximum likelihood approach. You basically, it's like using the EM algorithm, which wasn't out then, but you use outright allocation. It's called a hard version of the EM algorithm, because the EM algorithm uses fractional allocation. It's called soft assignment. So anyway, here's our expansion in terms of this is the cumulative distribution function of the normal, this is its density, and delta is Mahalanobis distance. And we've got this term A1 here, and this is the value of this term after the kth iteration. And if A1 was 1, then this would be the expected error rate just using the classified data. But when we actually include the unclassified data, we get a term A1, which comes out to be less than 1. We can prove H1 and H2 in magnitude are less than 1. So, I should say when Hills said this, he used the word bootstrap, maybe perhaps one of the first uses of bootstrap in statistics before Brad Efron came along. So anyway, this is, if you like, the excess error rate. It's less than 1 if mod, well, I should say the difference between the error rate just using the classified data minus the, I'm sorry, using all the data here will be less than 1, where this is just the error rate where the classifier is based on the classified data. And so when we worked out the relative efficiency of this, and this was a paper with Ganesh. I think I saw Ganesh's name here in the audience, well, logged on. And so this is only in the case, this is a univariate case here of the ARE. But in the case where the prior probabilities are equal, it holds for all values of P. And you can see that this ARE, on the numerator, we've got the excess error rate using a classified sample. On the denominator, we've got using an unclassified. So when the populations are weakly separated, you need about 200 times as many observations to do as well as if they were classified. And when they're moderately, we need about 10 times the sample size. So anyway, as I say, we got onto this because the EM algorithm came out in '77, and of course it showed the way how to treat these unclassified observations. We use the posterior probability to weight each of them. And I quickly became a fan of the EM algorithm. Now, we were fortunate that this paper got accepted very quickly when we submitted to Biometrica, because David Cox was the editor. He wasn't Sir David then. He ran a, because naturally, as you wouldn't be surprised to know that he was very efficient in running the journal. The paper got published very quickly, which was fortunate because unknown to us at the time, Terry O'Neill from Australia was doing a PhD at Stanford under Brad Efron. And what I think was useful was in 1975, Brad Efron had worked out the information matrix for logistic regression. So this is the joint probability distribution of a feature vector and the label. It's the mixture distribution of Y, that is, Y is unclassified, and then we've got the conditional distribution of Z given Y. So this is becomes, if we took samples now from that's partially classified, then the log likelihood based on a completely classified sample can be written as that one that's based on an unclassified times the log of the logistic regression likelihood. It depends only on beta. And so you can see that the information for theta will be for a completely classified sample will be the information for an unclassified one plus what it is for logistic regression based on completely classified sample. And so we can partition out beta and we get this result here. And so for a partially classified sample, which we can write like the information in beta, this m bar is just the average of these mj's. So if m1 minus m bar is just the number of, remember m is 1 if it's unclassified. So this is the mean number of unclassified ones in the sample, and this is the ones which are classified. And so if we take, now so Terry was able to get this thing here. This is the stumbling block in the multivariate case. How do you get this information? Well, if you know this, and we know this from standard multivariate theory, you can get the expression. And as I say, to make the asymptotic relative efficiency, this is the excess error rate, if you like, or the excess risk when you use this particular estimate for beta. And it's a consistent estimator. So the first order expansions in these terms are 0. But the leading term of order O1 in these expansions is 0. And so what this ratio here, if we take these, expand these up to terms of the first order, is just looking at the coefficients of 1 on n. So I'm letting this term here be the n times the inverse of the information in beta using a completely classified sample. And similarly, this would refer to the same thing for an unclassified. So that's how we work out. So this is how we work out these things. It is what we use today to work out the AREs that I'm going to be getting to. So these, I should say, in working out these results, we assumed that the labels are missing completely at random. So that made the problem easier than if they were missing at random but not ignorable. Now, what's the case where the labels are not missing completely at random? They're missing at random but they're ignorable. Well, that came up. This Dick Gordon here was a professor of medicine at UQ and an expert on people with, well, all particularly high blood pressure. Anyway, he had a lot of data where the features were truncated because they couldn't get a definitive label because of not being ethical to perform some invasive techniques. So just looking at one of the labels, we say, okay, we got an observation, yj. If it falls, say, less than k, we don't get to read what it is, or get to know its label. But if it's greater than k, we can perform some invasive technique to find out what it is. And you see, the probability that it's missing here is not depending on, it's not depending on any parameter. It just depends on yj and whether it's greater than k. And later on in 95, we worked out the ARE of it for p equals 1. You can see that when k is infinity, you've got a completely unclassified sample. And then as k becomes smaller, you get better asymptotic relative efficiency. Well, I'm up to 95. You might wonder, I might need the end of the lockdown to get to 2020, but no. So back in 95, from then on, I didn't really have cause to look at any theoretical problem in semi-supervised learning. Any problem that I had to do, they were missing at random, and the missingness could be ignored. And then this paper came along in 2015, and it using sort of weighted likelihood. They said let's form the log likelihood. We use any of the classified observations and form the likelihood when we ignore things, and weight it with the likelihood based on the unclassified ones where we ignore the missingness. And then we choose alpha by using BIC or AIC. And this, they had a small example, but in which they randomly assigned the observations to be unclassified or classified. It didn't. Well, the example didn't show if there's any gain to be, anything to be gained by using this method. And because I'm back now in 1977, but in JASA I did look at the case where we had a small number of unclassified observations. So rather than letting them go to infinity, I looked at where they were small and tried to get a weighting factor for the mean of those, say, that are unclassified and with the ones that had. But by the time this came out in 77, of course, the EM algorithm had been on the scene, and so that, yes. So, but Daniel and I looked at this problem, and we wrote up. This paper was presented at a meeting of the International Federation of Classification Societies held in Thessaloniki in Greece. But just briefly here, because we generated this data according to this logistic model here. So we took log of the probability of getting a missing label over the probability that it's observed to be a linear function of the entropy. And we generated that data, and you can see that the observations that are high in entropy are those falling in the regions of the feature space where the classes overlap. And then I'll go through this very quickly. We generated a number of samples. We fitted the full likelihood, which I haven't actually written down yet, and got a. Oh, they used the adjusted RAND index, so we followed them and used the adjusted RAND index. So we got an adjusted RAND index on average like that, and this is what you get: various values of alpha, and you can see it doesn't seem to be. Well, I think, of course, if you use alpha equals 0, you're using the likelihood, but assuming that ignoring missingness, the missingness of the labels, you're using the likelihood. So there looks to be no gain to that. Now, but that's how the likelihood for the ARI was for the full likelihood, and then if you use the likelihood ignoring the label missingness, it's down like that. But the advantage of this paper coming along was that Daniel actually started to look at some data sets which were unclassified, not artificially done by just assigning some of them. So this data set here and is from cytometry, and I'll put it up a bit larger here, looking at a few of them. These cells were assigned to 4 classes by a technician using manual gating, and the ones in black are the ones that he couldn't assign with his method with any degree of confidence. And you can see they are tending to be the ones that are of relatively high entropy. And there's another data set here where we have observations. There were 2 classes that there were people who supposed to have a normal profile, and the pathological ones, they had some disease, were the red ones, and the suspect ones, which the medicos were unable to make a decision, were the black ones. And then there's another data set here, a much smaller one. Oh, I should say this one had about 11,000 cells, and there were 333 unclassified ones. And the next one's got 670 observations, and with about 268 unclassified ones. So, and here's another data set, very small, about it's got about only 76 observations, and 23 of them were unclassified. So on the basis of this, the idea is we looked at minus log entropy here. I'll explain later why we use minus log entropy, but you can see that it tends to be smaller in the unlabeled class compared to the labeled ones. And well, we got this entropy by fitting mixtures of either t distributions or skew t, but I won't. And now we're modeling missingness for the unobserved class labels. So what does that mean? It means we've got to put forward a model that a label is missing given the data. That's the feature vector which has been observed, and if we want the probability it's missing, it means that Zj hasn't been observed. We don't know its value. So we take it to be the probability that it doesn't depend on Zj. So we're in the missing at random class now, and not the missing not at random. And now we take this to be a function of Yj depending on some parameters. And if this probability only depends on Xi, well, then we're in the missing completely at random thing. And so we can just go back and refer to earlier work. If it doesn't, but it depends on. I'm sorry, I should say if it doesn't. If it doesn't depend on theta and depends on Xi, but we've got a Yj here. We can't go. If it didn't depend on Yj, it would be, and not theta, it would be missing completely at random, and we could go back and refer to the previous work. But it's depending on Yj, so it's missing at random, but not missing at random because we've got rid of the Zj. But we've got two parameters here, and if theta doesn't appear here, then we can just ignore the missingness. But we've got theta here, and this is good because we want to get this information. We want to get the information from the missing labels to make up for the fact that the observations are unclassified. So we want to have this vector theta here, and the model we put forward is, and this model applies no matter how many classes we got or what their densities are. We take it to be a logistic function of the log entropy or the minus log entropy. And so here's the entropy of an observation with a reading y sub j. It's just given by the posterior probability of Yj belonging to the ith class times the log of that. And we sum over the number of classes. So we've got a model for that. And now in the case of two normal homoscedastic classes, if you do an expansion of the log entropy, it comes out to be a linear function of this discriminant function squared. And this is what we actually started out using when we only had two classes with a common covariance matrix. We thought we'd basically look at the distance between the classes. And so this is a square of the linear discriminant function that we're using. And so we used actually this d squared, but when you want to go to more than two groups, or they haven't got a common covariance matrix, so this becomes a quadratic, you can just put in the entropy. And so looking at the model, coming back here, we've got an Xi naught and an Xi 1 that controls the missingness. So if Xi 1 is very large in magnitude, it means that we're putting a lot of weight on the entropy. Now, now you can see here, we're plotting the probability of a missing label versus the posterior probability of belonging, say, to the first class. We've got two classes. So when that posterior class probability is near a half, the entropy should be very high. The probability of a missing label should be very high, because the entropy should be very high. And then as this is for xi0 to be 1.5, but then as we increase xi1, so this is minus 10 here. Now, if we reduce the magnitude of xi1 down to 5, then you can see this starts to spread out. And so it looks a reasonable model for handling unclassified observations that are unclassified because they're difficult to classify, not because they've been just missing completely at random. Now, so this term now refers to the log likelihood based on the classified observations. So the C means we're looking at the classified observations and we're going to ignore the fact of the missingness. So we just so we just write down the probability that an observation comes from the ith group or class, and then that's its density given that it comes from the ith class. And we've got this indicator function, which is 1 if yj comes from the ith class and 0 otherwise. And this mj is 0 if the observation is classified. So that's just the contribution to the likelihood from the classified observations, where we ignore the missingness. Now, if we don't ignore the missingness, we've got an mj equals 1 here. We've got the mixture density. And when we take the sum of these two, we've got the log likelihood formed from the partially classified data, ignoring the missingness. And so the full likelihood function that we propose one should use is to take the likelihood formed from the partially classified sample, ignoring the missingness, and then we add on this contribution from the labels n sub j, and so that they depend on theta. They've also got this nuisance parameter, which will reduce the amount of information, but it still gives us a chance to increase the information about theta in the problem. And so, and this log likelihood here, this is just like a binomial log likelihood. And of course, we've got what our model here is, how we take this probability that mj is 1, a label is missing. Now, the key theorem to this is to work out what the Fisher information is in the in this sample using the full the information about beta using the full likelihood. And this gamma now, this is the proportion of missing observations. It depends on theta and xi, and we can work it out. It's just given by the expected value over y of this Q function, the probability of a missing label. But coming back to this now, so the information about beta based on a partially classified sample using the full likelihood is what we would get in the ideal case where the data is completely classified. Now, because we've got unclassified observations, we lose this bit here. We lose gamma times the information in the logistic regression likelihood, but we gain the information about beta from the contribution from the missing labels. And so if the information about beta from the missing labels is greater than what gamma times what it is from the logistic regression, I've got to see here now, this is a conditional logistic regression likelihood. When we go to take the expectations, we've got a conditional constraint to observe. So if that matrix here is greater than that, that is if the difference between these two matrices have positive eigenvalues, is positive definite, I should say, then it's right. Now, this does happen. So let's have a look at if we look at some of these values now, on the numerator we put the excess error rate for a completely classified sample, and on the denominator we put it for the partially classified sample because we thought it would be larger than the excess error rate for a completely classified sample. But what you see here, a lot of these readings are greater than 1. This really surprised us. Sometimes they're less than 1, but look here, we've got a reading of 40 here, 23.4, 2.4. Of course, this is a value here that puts a lot of weight on an observation having a high entropy, relatively high entropy. So these were really surprising results. Now, in these results have been listed when the mixing proportions are equal, so they apply for all values of p. So we did a simulation experiment for p equals 1. So remember these values here, sort of like 2, 23, and 40. And if we go over here, and look at the values for that, we got 2.3. This should be 23, rough, and this should be 40 or 44, I think it was. But this is for a sample of size 500. So it's pretty good agreement that as least n gets very large. Now, we didn't worry about the ARE of the rule based on a partially classified sample when you ignore the missingness. So we're going to I don't know why my mouse is not working, but so we decided to work out the efficiency, asymptotic relative efficiency of this rule, where we ignore the labels, which are missing at random, and they're non-ignorable, compared to that as if we use a full likelihood approach. So we're going to get a very terrible result, because if having a completely classified sample gives you fairly low ARE relative to the completely classified sample, a partially classified sample, so would these. And you can see that these readings here are very small. So if you are in a partially classified samples situation, and it appears that you can do plots, of course, of these points. You can use principal components, mixtures of common factor analyzers to have a look at the data to see if it's a reasonable proposition that the observations that are missing are those corresponding to observations with relatively high entropy. Now, I've been talking about the observations being classified. I've been talking, that is, I mean that they're labelled. Now, what would happen? Well, what would happen if they had some misclassified ones? Well, you'd think that the rule based on the partially classified sample would do even better relative to a completely classified one which had some misclassifications. So so back in 1966, Tony Lackenbrock, who did his PhD on discriminant analysis and went on to become a well-known professor at, I think, University of North Carolina, and then to the Food and Drug Administration, etc. I was looking for something to do for my last chapter in my thesis, and I wrote this paper. Now, in case you're wondering about, I've gone back to 1972. This essentially is the last slide. I'm not going, I can't go back before 1972. This is my first paper anyway. But I worked out some modest theoretical results, asymptotic results, and they seem to confirm what Lackenbrock had been. But then, I was going to say the other day, in 2020, Richard Samworth, with I think a PhD student at the time, Tim Cannings, looked at this problem where you have imperfect training labels. I suppose in one sense it's good to see that topics that were relevant back in 1972 are still being worked on nearly 50 years later. Now, they do note in this last paper that sometimes misclassified observations is not such a having misclassified observations generally will have a detrimental effect in general, but sometimes in situations it may not. And we have this recent paper in CSDA looking at harmless label noise, where you've got informative soft labels. So, but basically, you know, if you generated your labels from the true from the multinomial distribution with probabilities equal to the true posterior probabilities, then you would have a sample that's got misclassifications, but it would do as well on average as if you had a perfectly classified. So, well, we wouldn't need a training sample, of course, if we knew the true posterior probabilities, but you might want to introduce a model like an hierarchical model where you have a Dirichlet multinomial model where you introduce a dispersion, a scale parameter for a random effect for over dispersion, and but that's for another day. And I think I'll stop there, and I'm happy to take any questions if that's possible. Thank you.
Thank you, Geoff. That was a great talk. Very, very interesting. Yes, we do have time for questions and comments. So does anyone want to unmute themselves and ask a question to Geoff? So Geoff, you can see in case someone wants to post something, there's a chat window that we can also open. I see that. Yeah, Ganesh, do you want to?
Yeah, I just want to say one word to Jeff. Jeff?
Yes,
can you hear me?
Yes, I can hear you, Ganesh.
That's very good presentation, Jeff. But I have a common question what we were discussing in those days, the convergence of this EM algorithm in this sort of unclassified situation. Is it the convergence is quicker, or how does it work for when many observations are classified?
Okay, look, I think it's relatively quick. I didn't mention that we have to use an expectation conditional maximization because the M step no longer exists in closed form for the. If we fix the xi, it does, but then we need to fit like a generalized linear model to estimate the xi given the theta. So so there's the M steps no longer in closed form for normal distributions. I should say this is ongoing work. We're still looking at. I'm not suggesting that in practical problems you're going to get an ARE that's extremely high, like 20 or something like that. We're looking at some simulations where using a quadratic discriminator function where you have normal population, say, with proportional covariance matrices. But
that is when the covariances are different.
Yes.
Okay. But thank you, Jeff. Thank you. It was a good presentation.
Good to hear you. Good to hear you.
Yeah. Yeah, I must thank Boris for giving me the chance to join.
I see. I'm glad I referenced your paper.
Yes, thank you.
I,
It was early, very early work, 1977.
78. Yeah.
Thank you, Boris.
Thank you, Ganesh. Is there anyone else who want to
The
ask a
reception here
question?
is not that good. Yeah, sorry.
That's okay. So anyone else want to ask a question to Joe? My comment when I was looking at your last slide, Joe, it was you know, as you said, like it's been like 50 years later, the primes are still investigated. So do you think there's still a lot to uncover in this area, or?
Well, I suppose I'm biased, or I think. Well, I think this does show you of course, Richard Samworth is a consummate mathematician. So and with his research students and colleagues, he's been able to look at perhaps things like support vector machines as well. I've only in this paper looked at you know two normal populations with a common covariance matrix. He's extended it to more difficult situations to handle analytically, and but I think there is. I think that, I do think in this particular paper there's a start of having a look at having because in this one you can think you could have a committee of experts, and each of them sort of puts forward a label, and then you aggregate their labels, and if they are really experts, you'd hope that their judgment is closely following the true posterior probabilities that we don't know. And if they are doing that, then we can actually increase the efficiency, or at least of a logistic regression. But,
Yeah, that makes sense. All right. I'll give a final chance to anyone to say something. I think everyone's you know, it's Friday and it's 5 p.m. so maybe everyone's happy.
Everybody want to go home.
Yeah.
I want to go out. I can go out.
Yeah. For us, go home is not a concept.
You are safe right now.
I'm still wearing a mask. I still have to wear a mask, and I'm basically I'm not going out to restaurants. So.
Yeah.
Yes, you all are locked down here, Jeff.
Yes. I've.
Very safe in Brisbane. I'm regret to go.